Morning. Hi, Kimmeline. Hi, Ezra. Hi, Downey. Morning, Charlie. Morning, Ava. Morning, Ryan. Hi, Hike. Hi, Hayden. Hi, Mason. I forgot who Spooky was. I'm sorry. So, a lot was posted this morning in Google Classroom in science. Something called a guided science application. We'll talk about that after we do our DNA. Your next DNA sheet was posted. That's obviously what you're answering today's DNA question, which is in these slashes, in these brackets. What is the relationship between its planet's mass and its surface gravity? So how strong gravity is when you're standing on the surface, or if you're on a gas giant, the strength of gravity if you're in the upper part of the atmosphere. So see the attached data table below with the highlighted information. Well, that means you see this, you click the picture, and I highlighted mass and I highlighted force of gravity in newtons. Pounds and newtons are units of force by gravity. Your weight can change, your mass can change too, but your mass can stay the same but go to a different planet and be a different weight. So you weigh a third of what you do on the Earth on the Moon, for example, right? Well, looking at the mass in these powers of 10, really, right? And looking at the weight in newtons for 1 kilogram would weigh this many newtons. How does mass relate to gravity? What is the relationship? Is it a positive relationship? Is it a negative relationship? Is there no relationship whatsoever? So that's kind of what we have to remember, what a relationship is. Positive relationships being both variables are increasing or decreasing. A negative relationship, one variable increases while the other decreases. Or the opposite is true. One is decreasing, the other is increasing. So if they work opposite each other, it's a negative relationship. If they do the same thing, it's a positive relationship. And if it's random, there's no relationship. Okay? So we're determining the relationship. And then when we review the DNA, we'll talk a little bit about the why, that relationship. So that's DNA number 1. The relationship between mass and gravity. Hopefully you can kind of already think of an idea. Morning, Eric. Good morning, Troy. I'll say Charlie again. Hello, Rainey. So you're working on DNA number 1. Your sheet is a little different. I've updated the rubric. You've probably already seen that. It was out of 9 points last week. This time it's out of 7 because I am dropping a DNA on Thursday. Instead, I'll be doing the DNAC on Thursdays. So your new DNA sheet, work habits, collaboration, and effort, they are suspended, essentially. However, effort and collaboration are going to be clear when you turn in the sheet or not. And then habits is going to be worth 1 point. So sheets are out of 6, 2 points for a very, very good answer, 1 point for basic information, and then 0 for nothing. So that would be 6 points. You don't need a 4th row. I forgot to delete that. Miss Kildoff's typing in the DNA itself for her students. So a little different. Online science notebook if we need it for extra notes. This is kind of blocked off now. Guidelines are down below like they always have been. G-Bucks are suspended. Alright? So that's just what the sheet looks like now. And you're obviously answering in box 1. while you're kind of working on that DNA, and I'll come back to it in a little bit, Mr. Hellman posted up the document that we've been working on for the last several days. No, it's fine. You were just typing in the question. It's fine. Let's kill it off. I just showing them the changes I made to the sheet. Teachers have been trying to plan a Friday where you guys can meet up. So a little different than Google Meet, a little different than a YouTube stream. We want to do this virtual hangout, this meetup for the Mighty Ducks on Zoom. Zoom is a little more feature-rich than Meet, in that the big reason why we want to use Zoom is it allows something called breakout rooms, which means you can have private little rooms in a video chat. Private in that a teacher's going to be in the room too, so it's private in that you can have different activities going on inside the same video conference. So you guys on Friday, you'll have a link and a password posted in Google Classroom, the Mighty Duck Google Classroom. I'll post that. You go to that link, you sign in with your Coventry account, you join the main hangout. From the main hangout, you can pick one of 4 things to do. You can go into the studio, or you can do a little bit of art with Miss Grant. You can go into the theater, watch a movie with Miss Kildoff. Go into the arena, play a game with me. Or you can go into our classroom and do a puzzle with Mr. Howman. Throughout the entire meetup, there's a spirit theme, like a spirit week. Picked hat day for this Friday. So this Friday from noon to 1:30, wear your favorite hat, your craziest hat. Join the video chat, see other people, talk to your friends, talk to people you haven't seen since March 13th, and then you can pick a place to go. So Miss Grant in the studio, she's going to show you guys and do tutorials on how to draw different SpongeBob characters. Miss Kildoff's movie hasn't been determined yet. Pick a movie, Kildoff. Competition in the arena, I'll be doing simple games to start. We're going to start with categories for Gladiator Pit. We're going to start with categories first. You don't know what that is, you can Google it, but you think of words for a category under a certain time limit, get points for the word that matches the letter that was chosen. It's all online, got a website for that. Alright. And then over in the classroom, Mr. Howman's infamous warm-ups. You can work on some of those. Alright, so that's the idea. Go to a Zoom chat, join the main hangout, talk to each other initially, share with what's been going on, and then go into one of the side rooms, do one of these activities, talk to people who want to do the same thing that you are. Alright, and then it's just something to do on a Friday. Obviously, it's an academic day, so you want to get your work done. If you're missing any work before noon, get that done, and then come on in. No one's going to be turned away. Even if you're failing a class. You do not compute? What don't you compute about? Yeah, questions, send them our way. Any of the teachers. Think of a hat you want to wear. I will definitely be representing my Giants, who just drafted a brand new offensive line. Hopefully there's a season this year. We'll see. So I'll be on Friday. Alright. To work. DNA number 1. TBD stands for to be determined. Maybe you can throw out some ideas. Some ideas in the future. Yeah, I saw the D2 kit. That was pretty cool. Good special team upside. Anyway, TBD stands for to be determined. If you have an idea, send it out there. You get an idea for a game that's school appropriate, multiplayer, isn't blocked, send it my way too. I was looking at a couple things, but a lot of them were on sites that, didn't need to be on. So, taking a look at mass versus gravity, I do have the whiteboard ready to go. But we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. We have our planets from our tour. We're including Earth this time. I want to rank them in mass, and then I'm going to rank them in weight, how much 1 kilogram would weigh on this planet. By ranking them, we're determining if the lowest mass planets have the lowest gravity, and if the highest mass planets have the highest gravity. And if they do, then that suggests a positive relationship. If they're opposite, that suggests a negative relationship. If it's all random, like random orders for both planets, then there's no relationship whatsoever. All right? So I'm going to start making a column, a little T table on my whiteboard. I'll show you in a second what it looks like. All right. It's a little messy. I can't make a table like you can. You can make a table in your DNA sheet. So you can go to insert, you go to table, and I'm making a 3-column, 9-row table. So you could actually insert that in. Table, 3 columns, 9 rows, so 3 by 9. And you can just plop this in, and then you can keep typing underneath it. So that's pretty useful. Mine's going to be messy, yours can be neat, right? And so planet number on the left, ranked mass, ranked gravity, low to high. So I'm just analyzing the chart. I'm not going to be going into the units and how mass and gravity, the actual difference. I'm not going to subtract the numbers. I'm just going to rank them. The lowest number to the highest number. What planet that would be. Okay? So under mass, which one has the lowest mass? So I'm going to look at the exponent first. The smallest power of 10. Mars is 10 to the 23rd. Mercury is 10 to the 23rd. But obviously 3.29 is smaller than 6.39. So I'm going to put Mercury as the lowest massive planet. On the DNA, instead of guidelines, you put a Q so it says quid lines. Has that been there this whole time? This is the first time someone's ever said that. It's been all like most of the year. Alright, it's fixed for next time then. Alright. Thanks. Can we do Snake? Send me you gotta email me a link of the game that you're interested in. I gotta take a look at it. Alright. So the lowest mass, Mercury. Alright. Go back to our chart. Keep going along. Obviously the next one was Mars. So those two were 10 to the 23rd. I want to go 10 to the 24th next. That's Venus and Earth. They're kind of, people who were doing Venus said it was the twin sister of Earth. That's pretty accurate. So 10 to the 24, 10 to the 24, which one is a smaller decimal? Venus is very, very close to Earth's mass and size, but it's a little smaller. So Venus is the 3rd smallest planet, the 3rd massive planet, and Earth is the 4th. Okay. So Mercury, Mars, Venus, and Earth. So we're going from the lowest mass to the highest mass. Mercury, Mars, Venus, Earth. And so you're putting in Mercury, Mars, Venus, Earth. right? This is just rankings. But this is not the highest to the lowest. I'm going lowest to highest. All right, and then you can put those in. Hopefully straightforward. So now let's finish out the rest. So the solar system, 10 to the 24th. How about 10 to the 25th? Is there a 10 to the 25th? Uranus, smallest of the gas giants. How about 10 to the 26th? We have 2 for 10 to the 26th. Neptune and Saturn. Saturn larger, 5.68. Neptune's 1.02. So we'll go Neptune and then we'll go Saturn. And then the big guy himself at 10 to the 27, Jupiter. Not enough mass to be a star. If you watched what happens when the gas giants collide on my channel, you need 0.08 solar masses to be able to conduct fusion at the core, enough gravitational attraction and pressure to fuse hydrogen to helium that is on that planet. So 0.08 is about 8% of our sun's mass. Jupiter is about 0.01. So it's 1% of the sun's mass, roughly. Therefore, Jupiter cannot conduct fusion. It needs a lot more mass to do so. So, even if you had all the gas giants colliding together, that's not enough mass to cause fusion. Alright? You need something larger. An object that is in between a gas giant like Jupiter and in between a star, so not a lot of mass and a lot of hydrogen, but not enough to fuse, is called a brown dwarf. Brown dwarfs are the in-between planets and stars. Alright? So we just ranked mass. Mercury, Mars, Venus, Earth, Uranus, Neptune, Saturn, Jupiter. What we want to do now is to see if gravity matches this order. If it's flipped, if it goes Jupiter, Saturn, Neptune, Uranus, Earth, Venus, Mars, Mercury, it's opposite, it's a negative relationship. So that would mean more mass means less gravity. Or if it matches this order, it would mean that it's a positive relationship. If some planets are out of order, we'll have to take a look at that. Alright, so we go back to our data. The lowest amount of gravity, it's a tie between Mercury and Mars. So, kind of put them in between. The second, next highest number, four, 8 is Uranus. After Uranus is Venus. 9, 10. We have Earth and then Saturn. Higher than 10, we have Neptune and then Jupiter. So for the most part, we seemed to be matched up. So Mercury and Mars seem to be on the same gravitational scale. So does Venus and Earth, Neptune and Jupiter. They all seem to be roughly equal in terms of matched up with their gravity and their mass. But there's a couple of outliers. The big one, like, why is a gas giant so low in its surface gravity? Same thing with Saturn. Mercury and Mars are not really a tie, but we're going to say that they're in order. So for the most part, there is a positive relationship with gravity, surface gravity. Okay? So I'm going to write for the most part, there is a positive relationship between mass and surface gravity. Okay? So that suggests as one increases, so too does the other. If one decreases, so too does the other. Okay? Both increase. So what's going on with Uranus and Saturn? Those of you that did Saturn, hopefully this doesn't sound new to you, but these two are the least dense planets in the entire solar system. So they have a lot of mass, but they take up a huge amount of volume. Yeah, I'll move my webcam. Yep. It's kind of messy. If you have questions, I can rewrite it. So Uranus and Saturn are very, very low in density, and this kind of plays a fact in, again, we're looking at surface gravity. I kind of just generalized to gravity, but this is force of gravity 1 kilogram on the surface. Uranus and Saturn also don't really have a defined surface. That's another issue. Uranus and Saturn are outliers because of their very low densities. Sometimes people will say, or you'll read, or you'll see that if you could put Saturn in a bathtub, it'll float. Saturn's density is less than 1 gram per cubic centimeter. So yes, the planet Saturn would float in a bathtub. It would float on water. Uranus kind of falls in that pattern. But Neptune and Jupiter's so large, Neptune is so dense that they follow gravity with their mass. Neptune's is sometimes called an ice giant instead of a gas giant because a lot of its material is in an ice state around its core and makes it very dense because solids are denser than gases. Or even liquids, which might be around Saturn's core, right? Or Uranus's core. So for the most part, there's a positive relationship. As mass of the planets increase, so too does their surface gravity. And so that's DNA number 1. Again, there were only, as you're finishing this, there are only 3 DNAs this week and for the foreseeable future. DNA 1 on Monday, DNA 2 on Tuesday, DNA 3 on Wednesday. Review, quiz, and whatever work we need to keep doing on Thursdays. So you can delete your row 4 on your DNA sheet number 25. Well, what's next on our agenda? Introduction to the GSA and its rubric. Choose an application and complete phase 1. Oh boy. What does this mean? Guided science application. Yes, they are. Downey. Guided science application number 1, exoplanets. Choose one of 3 possible applications on exoplanets: a research CER, a pre-designed experiment, or a theoretical prototype or prototyping. Once chosen, some limitation is going to be possible. I'm going to get into that in a second. You're going to delete the other things that you are not doing, and you're going to complete phase 1 through 4 under guidance for this assignment, which I'm planning on being done around Wednesday of next week. So a longer project, but a project of your own choosing. So let's open this up, then I'll go into the rubric. Move this out of the way, get a little more space. Planets beyond our solar system are known as exoplanets, or extrasolar planets, because they orbit another star that is not our sun. So we're now talking about, or thinking about, other solar systems. There's another 300 billion stars in our own galaxy. Around those stars, most of them have planets. We haven't discovered them all, but we can find them, and this is kind of what we're going to lead into. Characteristics of discovered exoplanets are wide-ranging, partly due to their methods of discovery. There's 2 primary ways to find an exoplanet. You can either watch to see a star wobble in the sky, and that wobble means that a planet is tugging on that star, and the amount of wobble that a star does determines how much mass that planet has, because that's how much gravity is pulling on that star. Or you can have a planet move in front of a sun or a star, and that's called transiting. And you can determine the size and the material and the composition of a planet when it moves in front of a star and dims its light by a fraction of an amount. So there's 2 ways to find that. You either need a planet that makes a perfect alignment with the Earth and the star that we're looking at, or you got to watch a star wobble. Very small movement back and forth. Exoplanets are busy fields of astronomical and planetary research because they engage our imagination of a planet like Earth that could be home one day, or a location for life to exist outside what we currently know. And so I linked in 2 videos to kind of explore this idea. A high school student who interned for NASA a few months ago discovered a new planet, a high school student. And then my video on does the sun have a shadow, because this video leads into application B. So let's see if we can listen to this. Three minutes.
A lot of us in high school might have learned how to write a better sentence, solve math problems with variables, read Ralph Ellison's Invisible Man, and Lincoln's second inaugural address. NASA scientists announced this week that a high school senior from Scarsdale, New York, named Wolf Sukier, has discovered a new planet. Does he get extra credit? Mr. Sukier made the discovery just 3 days into his internship with NASA's TESS, the Transiting Exoplanet Survey Satellite mission last summer. He joins us now from Scarsdale. Thanks very much for being with us.
Yeah, and everyone's in Winnevo. But yeah, this is the student who found that exoplanet. So TESS, the Transiting Exoplanet Survey Satellite, this is a satellite that looks at stars to see if planets move in front of them, and monitors their starlight to see if there's an exoplanet.
Thanks for having me.
I don't think I've begun an interview with anyone like this before. Please tell us about your planet.
So the cool thing about this planet is it's a circumbinary planet. So what that
Star Wars
means is the
fans.
planet orbits 2 stars at the same time. So if you think to Luke's home planet in Star Wars, Tatooine, it's similar to that. Each day on this planet, you would see 2 suns rising and 2 suns setting.
Does the planet have a name yet?
It has the boring name of TOI 1338b.
Someday will they call it Wolf, would be my question.
That's what my family wishes. Wolftopia.
But I mean, how far away? Is it possible to visit?
Very unlikely. 1,300 light years away, so that means even if we were to have a spacecraft at the speed of light, it would take over 1,000 years to get there.
1,300 light years away. So even if you had a spacecraft the speed of light, it takes 1,000 years to get there. That's how big space is. Remember, the light that you see travels 300,000 kilometers per second. And it's instantaneous when you turn it on in a room or whatever. But in space, 'cause it's so big, it takes forever to travel at that speed. And this name, TOI 1338b, this is the name of the star, TOI 1338. B is the designation for any planet. So for example, there is an exoplanet around our closest neighbor, Proxima Centauri. So the name of the exoplanet around Proxima Centauri is Proxima Centauri b. A would be the star, but we don't name a star as A.
There, or any form of life.
Also, incredibly unlikely. The brighter of the two stars that the planet orbits is brighter than the sun, and also the planet orbits at an orbital period just longer than Mercury's.
Were you just looking out the window? I mean, how did you discover a planet?
So the TESS telescope observes the sky, and the star system happened to be one of the stars that TESS was observing. So what happens is the planet, when it orbits those two stars, will pass between those stars and our telescope. When that happens, we notice a dimming in brightness from the telescope. If you imagine the moon eclipsing the sun during a solar eclipse, it's a similar phenomenon.
But it's
So
called a
I noticed
transit.
that dimming of light from the stars, and then that was evidence that something was there, and it turned out to be a planet.
Did you go running to the older adults, the established scientists, and say, wait, I think I've discovered a planet?
Yeah, so this was one of about 100 targets that I flagged on my initial looking, but this one was the best out of them. I probably put about 10 asterisks next to it in the spreadsheet that I went over with my mentor, but like the whole research process is far beyond what I would have imagined. The amount of people that were involved in confirming the planet, making sure it's real, characterizing the planet, so getting how long it orbits and whether or not it will still exist around the star in the next millions of years. All of these things I didn't know before starting research.
What fascinates you about the stars, the heavens?
They're unknown. There's so much there that we've yet to explore and catalog.
You are senior. Do you know where you're going next year?
I'm still figuring that out, but my top three choices are Princeton, Stanford, and MIT.
I've heard of them. You put this on your student
So,
application? Discovered
big
a
top
planet?
three choices right there.
Under what? Hobbies? Internships?
Activities and extra information.
Wolf Sukir is a senior at Scarsdale High School. Thanks so much for being with us, and congratulations.
Thank you.
So pretty cool that someone, probably about, I don't know, 5 years away from you in age, discovered this past year a planet. Does the sun have a shadow? This episode of Ask Mr. G.
I'm going to kind of
People
skip
in
around,
Chat
and you
of
guys can
mass
check a look at
spectrometry,
this later.
in which is a on the other side of the spectrum, below
But remember
red is
that
infrared,
light
and then
obviously
below
can be
that,
split.
microwaves, and then real highest energy on their chemical.
Not too far.
Have it refract the light into the spectrum and other prisms to get a wider range of that rainbow effect. And so before becoming a teacher, my focus was the different chemical each of these prism. I'm going to take sunlight and I'm going to put it into a prism to refract the sun's actual light, but then analyze it in greater detail. And so he took the light from the sun given off at the photosphere, and what he found out is there was not a complete spectrum of violet to red. And So this scientist took a special prism and took sunlight and broke it down and found out that there were black lines or missing parts of a rainbow. And so that spectra, with these absorption lines, determine that you can look at compounds from a star and figure out the composition of a star. And so what we're doing now with NASA and the James Webb Telescope is we want to see if A, we can find other sun-like stars, but B, also find another financial issue, but we're hoping that it finally is launched in 2021, about a year from now, March, February. And this telescope's going to be in orbit around the Earth, and it's going to look at other stars, and especially stars with exoplanets, planets not part of our solar system. And the James Webb Telescope is going to wait for this planet to move in front of its star, almost like an eclipse, but it's called a transit, and it's going to allow some of that starlight to go through that planet's atmosphere, and just like Joseph Fraunhofer looking at the spectra of our star, our sun, and analyzing its signature, the James Webb Telescope and the astronomers working at NASA and around the planet are going to look at the spectra of exoplanets. And this spectra from the exoplanet will allow us to look for, once again, those compounds and molecules that have certain signatures in energy when received from an outside source. So think of this as a really large nature-based mass spectrometer that will look for organic compounds on exoplanets. And so you can watch that a little longer, full idea, if you're interested in doing application B. So what are the applications? Again, you're going to pick A, B, or C. And for the next almost over a week, you're working on A, B, or C, whichever one you pick. You're not going back and forth. So if you pick one, technically you might be able to have enough time to switch out tomorrow, but after tomorrow, you're locked into either A, B, or C. And then what you do is you type in which one you want to do, A, B, or C. Type in what's in parentheses here, or quotes, sorry. And then you work on the color or the letter that you see for the rest of the document. And if I'm doing A, I can delete this table because I'm not doing B. And I can delete C. I can just work on the red tables. All right? So that's once I make my final decision. So I'm going to go into that, Jake. All right? What does each one involve? Application A. The topic, habitable exoplanet criteria. You will be researching on your own what the criteria needs to be for an exoplanet to be declared habitable. So research a concept from the topic, habitability of an exoplanet, that you use to answer a question in a CER. So things like, does an exoplanet have a tilt like the Earth? Does an exoplanet have a moon like the Earth? Does the exoplanet have a distance from its star like the Earth? Is the star that the planet orbits the same as the sun, or is it different? Are there other planets in this solar system like Earth has in its? So different criteria, things that you know about the Earth that we've been doing all year long, tilts, rotation, revolution, distance, now in the solar system, habitability, things like that, for weather. Does that exist on your planet? What makes life possible on an exoplanet? What makes Earth special is what you're focusing here. But you're writing a CER. You're using the ACES format to answer the question with a claim. The questions further down below. Cite sources, explain sources, and summarize. All right? Application B. Application B is hands-on. So this whole assignment was me trying to think of a way to get you guys to be able to do something hands-on at home. This is my workaround because I can't guarantee everybody has the same materials. So my goal was originally have you do something like application B, but if you can't have the materials, you don't have the materials, then you got to do either A or C. So look at application B. I'm going to show it to you in a second. If you don't have the materials, you got to do A or C. If you have the materials, you can do B. You don't have to do B if you have the materials. It's your choice. It's your comfort level and your choice. But application B, this right here, requires certain materials. If you don't have them, you can't do them. And so what you're going to be doing is, kind of like the James Webb Telescope, you're going to find the spectra of other light sources to either prove or disprove that we can use the spectra of stars to find sun-like stars. So you're proving that spectra are unique to different stars. It's a pre-designed experiment, and I'll show it to you in a second. All right. Application C, you are designing a theoretical interstellar spacecraft. And that means working with the constraints of interstellar travel. What issues exist with interstellar travel? Design a theoretical prototype in Google Draw, or if you're familiar with the SketchUp website program, you could also use that to blueprint your own spacecraft. 2 options, and then you pick a final option and tell me why you picked that one. All right. So application A is a CER, criteria of a habitable exoplanet. B is an experiment, but you need the materials to look at light. And then C is blueprinting a theoretical or hypothetical interstellar spacecraft. And then you choose. But don't choose yet. Wait a second. All right. I already answered that question, Ryan. I'll get to that at the end. All right. So you're going to be doing phase 1 today, answering this question. But I just want to show you in part B, doing your own research for the CER. This right here is what you're making if you want to do part B. Okay? You're making a very simple homemade not mass spectrometer, I misspoke, a very homemade spectrometer, simple spectrometer, looking at light. And so you need a cereal box, scissors, probably have scissors, half of a blank CD. You don't need half of a blank CD, a full CD works, but also I think, I was testing it a couple times, a DVD or a game disc would work too. You don't need a CD, because I don't know how many of you have a CD. However, I emphasize this, don't use something if you're afraid of it getting scratched. I'm not saying it's gonna get scratched, but this is dependent on how rough or how gentle you are with the disc. Okay? So don't take your favorite game out of your PS4 or Xbox and then shove it in the box and then get scratched and you can't play it. Blame it back on me. All right? If you have it digitally, then go right ahead. I'm not risking Skyrim. You can play Skyrim on a refrigerator now. I think you can risk Skyrim. Non-clear tape, so masking tape, duct tape. I was using painter's tape. All right. You want to seal up any holes. You only want 3 holes in the box. And then you need access to different light sources. So like ceiling lights, a window, a candle would be cool to see if you could do that. Again, safety. All right. How would you make it? Cut a small square hole on top of one of the sides. That's your little viewing hole. The second, you're going to cut a slit into the box at about 60 degrees. So this right here. That slit allows you to insert the CD. And then you got to cut a clean hole horizontal on the opposite side of where the CD is. Okay? The cleaner the cut of that slit right there in step 4, the cleaner it is, which means not as rough, the better you're going to see. Right now, I'll tell you, and I try to make 2 of these, and my wife is upset with all the cardboard boxes that have been on the dining room table the last couple weeks. This is the hardest part, making the angle with the CD and inserting it in. And you gotta get the angle just right. and you'll be able to see a rainbow. And so the material that's used to be able to record data on a disk refracts light because a little laser reads a CD. So the different wavelengths of light allow it to store information on a disk. So you're using that function of a disk to be able to refract light like a prism. Okay? So you're trying to refract light like a prism in a dark space so that you can look to see if different light sources have different fingerprints, different spectra. When you try using this with sunlight, do not point this at the sun. You don't need to burn your retina. You won't feel it, by the way, but just don't burn yourself in the eyeballs. All right? Try ceiling light, try a flashlight, try sunlight through a window, and then for 4 points out of 4, find me something additional on your own. A candle. I think that could work. I think of some other weird sources. A candle. If you have a street light kind of nearby during night, you can try a street light. Moonlight is just sunlight, so don't bother trying to use a full moon. What else could you use? A screen maybe from a device. Like if you have a big TV, or you can put your phone kind of near it, not the flashlight side. See if a screen produces certain wavelengths of light. Without night filter on, by the way. And then maybe, I don't know. You probably won't be able to see it, so never mind. Fire. Fire is like a candle. So yeah, like a fire or a candle. You could try that too. All right. So that's application B. Is probably the one that I originally was hoping people would do because it's hands-on, and I want you guys to do something hands-on instead of just listening to me and you guys answering and writing. So think about application B. And if you're not comfortable with trying to make something, you don't have to do it. You can do A or C. You can do a CER, or you can do some design work building a spaceship. All right? So don't feel like you have to do B. If you don't have the materials, it's not a big deal. Just do either A or C. All right? C is a lot of research too with B. All right, phase 3, you're doing an outline for the CER. You are drawing, though, for me. You're taking pictures, you're drawing the spectra, and then you put them in a stack and you look for a relationship. All right, like which light sources produce which types of light. All right. Application C, you're drawing a blueprint for me, either on paper or online, giving me an explanation for it, labels, dimensions. And then you're writing your final CER, conclusion, you're writing your final paragraph of what you found, and then your final design, your final product. All right? So these are the 3 applications. I'm anticipating this whole thing due, phase 1, 2, 3, and 4, next Wednesday. All right? Today, you're all about choosing which one you want to do, and then answering the question that I assigned each one for phase 1. Phase 1's short. It's just answering a question. But this question helps determine what direction you're going to go in your application. All right? Tomorrow, you can delete the other colors or letters that you're not doing. So this document gets a little smaller. It's not as big as you are seeing right now. Okay? So right now, we have about a little less than 10 minutes. Go ahead, pick an application, type it in, do phase 1. What are the criteria for a future human colony on an exoplanet outside our solar system? What would a planet need, you think, in your own opinion, what would a planet need to be able to support human life? Application B. Can light be used to identify its source? I would go watch Does the Sun Have a Shadow to help you answer this question. Application C. What challenges might exist in sending a spacecraft to the closest star to our solar system, Proxima Centauri? What challenges, what hurdles are in the way? We talked earlier today that it's 1,300 light years away from that guy's planet that he discovered, that senior in high school, which is like Tatooine. 1,300 light years away. Even if you travel the speed of light, it would take you 1,300 years to get there. So clearly the biggest initial hurdle is distance. How do you get something so fast, or how do you deal with the big distance? So that's just a challenge. I'm not asking you to solve it right now. That's later. I'm asking you just to address the challenges. Name the challenges. So you are doing either A, B, or C. You are not doing all three. Can't emphasize that enough. Do not do all three. You're doing one or the other. A, B, or C. So pick and do phase one. So phase one is today. We'll do phase two tomorrow and Wednesday. We'll start phase three on Thursday, but not finish it. While you're working on it, kind of just like listen. The rubric, I'll be going over this many times in the future, but just to kind of show you, I did combine your CER rubric, lab publication rubric, and using rubrics from engineering projects, I looked for similarities between all three. Looking for similarities between them all, I found phase one, phase two, phase three, and phase four. Phase one is always trying to set the direction of what you're doing, basically making a claim. Your second part in doing a lab or doing an engineering project is testing and collecting information. That's like research in a CER. Assessment of information. So when you start to analyze data, when you start to take a look at the data sheet or have a Socratic seminar on which projects did really well and which ones didn't do so well, that's assessing data. That's assessing information. That's explaining your information and assessing your claim. So there's very clear similarities and connections between those three things. This rubric is like the ultimate rubric for everything that we could do in science, really. You are not building tomorrow. Actually, I'm sorry. Yeah, because you're doing phase two. You're going to start building tomorrow. I'm sorry. Yes, Downey. And then usually at the end, you provide a conclusion. That conclusion is a summary. You're defending your prototype. You are explaining your experiment. You are defending your claim. So this is your defense of your application. So phase 1, 2, 3, and 4. It's just like ACEs, just a little more general because I pulled in things from your labs and engineering. The last three do not change because all three require you to write at the end. I will be assessing your writing style. Because all three require you to write, I'll be assessing what vocabulary you use. And because all phases and at the very end requires you to write, I'll be looking at how you actually use the English language. And so this rubric should be very familiar because it's similar to everything you've done. Out of 24 points. Wednesday before midnight, I'm looking at the deadline. All right? So today you're just doing phase 1 and you are doing phase 2 tomorrow. So if you're interested in doing application B, you are doing application B right now. I suggest today you look for a cereal box, a disc you don't care about, and make sure that there's tape in the house that is dark, not clear. So masking, duct tape, painter's tape, things like that. Ask your parents, ask who's at home if you can borrow that nicely. If you do not have it, do not send anybody out to go and get it. Don't go out of your house to go get it yourself. It's fine. You can do A or C instead. scared myself. Go from quiet to that, huh? So if you haven't done it already, that's what you're doing today for the rest of today. You're doing phase 1. You are picking what you want to do and kind of guiding what you're going to be doing for the rest of a little over a week. All right? Remember that Friday we have a meetup. So kind of talk to people. Try and build up the hype. Pick out a hat. All right, someone asked if the Giants ever going to be good again. Just you wait to see what happens to the Patriots. You know, the Giants going to be good again. Is the Patriots like era over? Is it done? That might be interesting. You know, talk about. You got questions? Stidham's time now, huh? Okay, Stidham who? What? You got questions? Send them through email, send them through Reminds. Have a good Monday. Bye, Rainey. Bye, Ava. Bye, Ryan. Bye, Hike. Bye, Troy.